We're going to get started here in just a moment. We've got some great content for you today. Just checking out the stream. Seems like it's working fine. But what we've got is we've got this power supply. We got it off of Amazon not too long ago, and we're just going to open it up, unbox it, take a look at how it looks inside. This unit off Amazon, I think it cost $50. It was, and honestly, I'm not expecting too much from it, but for $50, I mean, how bad can it be? And well, I guess we're gonna find out how bad it can be for $50. So we're gonna get started here in a moment with the unboxing. But yeah, this is a Tech Power 30 volt 6 amp power supply. We're going to exercise it pretty fully. We've got some loads off camera here. Features that they list on the side of the box are a one-way output, which I suppose is probably good for something that's power supply. There are other supplies capable of syncing or sourcing current, and those can simulate more like a battery, but this is just getting a power supply for the shop. We don't need anything too fancy. Automatic temperature control system and radiation system, which I'm hoping they mean fan, because I would rather them not dump radiation into my room to cool this thing down. And the device is stabilized, short circuit proof. That's really the whole reason why we got this lab power supply. With a typical voltage regulator, what happens is you have your voltage regulator and it's regulating voltage, not current. What this allows you to do is set a programmable current limit, so that if you have a fault in your circuit while you're testing it, the current limit will come into effect, and that will prevent damage to your circuit. So for example, if you want to power on a circuit, like our inverter that we're building for Project Darwin, we're building a full uninterruptible power supply for that project. If we wanted to do that, and we want to power up the board at light load, we can use a supply like this to power it on at very light load with a current limit of 100 milliamps, and if there's a short somewhere, there's a fault, the current limit will come in and save the day. Then when we want to do more advanced testing, we can crank up the current limit, so when we load down that circuit, it will still function correctly. So that is why we bought this supply and what we're doing here today. First things first, saying we've got the Tech Power product here. They say it's a regulated power supply. They say that we've got the highest version they have, which is the 30 volt 6 amp version. Let's see what other goodness they have in here. General description: your new DC regulated power source provides accurate and stable DC power. That's certainly ideal. So you want for test benches, labs, schools, repairs. Yep, this all looks pretty standard. Ooh, specifications. We're gonna keep this handy. So it looks like on this piece of paper, it looks like they're giving us some specifications that we can use to test out this supply. They're saying that we should have voltage regulation up to 1 times 10 to the negative. Okay, so the voltage set point times, is that 0.1%? Wow, that'd be awesome. And then plus 3 millivolts, which is probably going to be more than that most of the time. Then the current regulation is a little worse. Ripple and noise, 1 millivolt RMS in constant voltage mode. I'm pretty sure it's not going to be that good, but we'll still test it out. And it tells you how to use the knobs on the front, same as any other power supply. We'll set this off to the side. Alright, what is this? 1-year warranty, purchase registration. Well, I'm pretty sure they won't honor this registration if we tear it apart, so that's useless anyway. Let's throw that right in the trash. Alright, in the box, looks like it gave us power cord, and I've always found that the power cord starts to give you a great idea of how cheap something is, this one's actually not too bad. I've certainly received worse power cords. I bought a power supply off Amazon for, I don't know, maybe $3 once. It was pretty incredible. And when I pulled that power cord out, it felt like it was just a fire hazard. This one gives me some confidence that the ratings on the side are accurate. And in this case, that looks like it's a 300 volt, 105C rated supply. Not seeing a UL marking on this cable. No UL mark, but it is an 18 gauge cable. Oh, no, there's a UL mark. Look at that. UL listed cable. That's better than I would have expected for something like this. And these are nothing standard or nothing special. They're just just some wires. I don't know if I'd really want to put 6 amps through these. They're kind of anemic. They've got, yeah, I mean, maybe. I don't think I'm really going to use these. But, yeah, I suppose it's a nice touch if you happen to be buying a lab power supply and don't have any sort of, place to plug in a cable. Alright. There we go. Get that box out of the way. Here we are. Pretty nice packing materials. They've got a nice open cell foam. It's better than the styrofoam that gets everywhere. Whoa. I tell you what, it's definitely a linear supply. This thing is heavy, and that's what I would expect. For something that can pump 300 watts out of the front, I would really expect that if it's pumping 300 watts out the front, it needs to be heavy. As we're going to talk about in an upcoming video, actually, we designed this custom transformer, and we just walked through 3D printing the bobbin, and I've got a video coming out soon about how we wound this and designed the actual transformer. And this transformer here can handle almost 1,000 watts, and it's very small, very light, and that's because this is a switching transformer. It's made to be switched at 100 kilohertz. This uses much larger magnetics that are designed for line frequency or lower frequencies. In this case, I do suspect it is line frequency. But of course, I'm saying that having never looked at it, so I suppose we'll find out. Looking at how it was received, looks like that closed cell foam did a great job of protecting this during shipping. Yep, there's that line frequency transformer that we were just talking about. It looks like they've got a couple bolt hole patterns here, so they're really doing a great job of leveraging one enclosure and bolting in whatever transformer makes it whatever power level you bought, which is great to see that they use some forethought to save some money in manufacturing. Manufactured in China. Looks like they're telling us that the fan will turn on when the product exceeds 50 degrees. Yep, radiator fan, that's good. No, I'm just kidding, I knew it was a fan. And the serial number for our product. Yeah, looks pretty good. Looks pretty good. Alright, well, wouldn't really be doing my job here if I didn't take this apart before we turned it on. So let's go ahead and do that. Thankfully, this supply is built in such a way that they will never ever know that we took this apart. They don't have a label or anything. It's almost like they were asking us to take this apart. those playing along at home, I don't think I said the model number, but this is the Tech Power TP 3006D, 0 to 30 volt, 0 to 6 amp, DC regulated power supply. We got this one off Amazon, but honestly, before we did that, I wanted to check out their website to make sure they were a company that I could have faith in. And based on their website, you know, they've got all kinds of linear or other power supplies on their website. It seems like they've been in the business for a while. They're just not one of the big players. Like, they're not something that you would see in a professional lab. But hey, this is all about what options are available to beginners. And you know, honestly, if I were starting out, one of the first things I would buy is a nice lab power supply. There's nothing more frustrating than spending so much time designing a circuit like this and then just, blowing it up by not having the right power source. You need one of these in the shop. The only thing I would prioritize over getting one of these would be a multimeter. A multimeter is absolutely critical, because if you don't have a multimeter, how are you even going to begin to debug something? It's just not going to happen. So, yep. Let me get this out of the way. All right. What in the world is this? Oh, that is really a pain to get out. But I can see it's a standard glass fuse. They've got a slow blow fuse in there, 5 amps. We actually recently just bought a fuse kit for our latest project effort, so we will have plenty to do there. Looks like the wiring here is pretty solid. They've got some high temp wire coming out, this kind of glass, or the kind of wax paper insulation there. Some nice sleeving around their supply. You can see in there some clear sleeving. Their diodes for rectification look pretty good. They've got some relays. So that's probably switching in and out some taps here. Based on what voltage we request here, it probably switches taps in and out on this transformer. And what that'll do is that'll allow the linear regulator up front to actually, nope, the linear regulator out back, right by this beefy heatsink. It'll allow that linear regulation portion to be the most accurate. And actually, that makes a lot of, looking at how this is laid out, definitely that is how this is architected. So you can see that the transformer control, switching these taps in and out, that has been done on the same board that actually performs the regulation, and you can tell because I've got this huge heatsink right next to the fan, and then all the controls are up front. As a first thing that I noticed, this connector was kind of half unplugged. That's not great. Back here, they've soldered wires onto a place where there's a crimp terminal, or there's supposed to be like a mating connector, and they just didn't bother with any of that rubbish. Definitely this thing was designed down to a price. This feels like high temp hot glue rather than Celastic holding the holding this cap in place. That's just hot glue. Some heat shrink holding these wires together. I like this fiberglass insulation on the main stuff. Got our MOV. Looks a little anemic, but hopefully the power is pretty clean here. And this seems to be that main power switch. That's got a nice click to it. On the control board up front, looks like for the current shunt, they've opted for some kind of known resistance wire with a known length. Ooh, their ground lug. Oh, I don't like that. They soldered the ground lead onto a screw That's not great, and that screw is actually the back of the binding post. Rather than crimping it onto something and screwing it down, they opted to solder it to that post, but these posts do feel like they've been adequately tightened. I got some good short cables going between these two boards. Wouldn't want to see that too long. Yeah, honestly, not a whole lot of complaint here. They've got adequate heat sinking, I'd say. Nice big rectification diodes. I have every reason to believe that this can output the 300, well, it's probably about 270 watts or whatever this thing's rated for. Seems like an appropriately sized transformer and output stage, so as long as the controls up front aren't terrible, we'll be good to go. Speaking of those controls, looks like we have, what do we have? Are these LCD drivers? I see ICL 7106 CM44 LD907 DWZD. Two of those. One per display with a variable resistor that's probably setting the backlight. Those are 7-segment displays on little, I call them zebra strips. I think that's really what they're called. At least that's what I learned for them. One last check before we move on to putting this case back together and powering it up. Let's go ahead and make sure that this switch is opening neutral, or opening live, not line, not neutral. So the way that we're going to verify this is by taking this front panel, plugging this in, and we're just going to check for continuity inside the unit. Set up our multimeter, the continuity mode. Alright, verified that it's configured correctly. Okay. So let's just see which switch is open. Alright, so we have this off. It's a little bit of a stink inside of here, just like that kind of Chinese stink. That's not great. Yeah. Well, actually, before we do any of that. Whoa. What? So, alright, let's measure the impedance here. Is this the transformer? Is that what this is? Oh boy. This might be interesting. I'm measuring from line to earth, and I'm measuring 2 ohms when I put that switch in. I am hoping, I'm desperately hoping, that that is the primary winding resistance. Alright, but yep. Given that this thing might be about to burst into flames, let's do a little bit of diligence here and screw this case back together before we power it on. Yeah, so looks like we got a couple people watching. Looking at the comments, if anyone wants to drop some in there, we can definitely be distracted for a little moment. But yeah, just thanks for tuning in this morning. Hope everyone's having a great week. Yeah, I know for me, this video has been on my back burner for quite some time. I've been meaning to get the live stream set up again, and yeah, I just haven't been able to get around to it till this morning, of course. What it is, well, we've actually been having some issues with our latest endeavor, that Project Darwin, our UPS, for those who don't know, uninterruptible power supplies, are systems which allow mains connected equipment, like a computer, to continue to operate when the power company fails to keep the lights on. And it does this by storing some energy in an alternate source. In our case, we're planning on using some lead acid batteries, but it stores up some energy in those lead acid batteries, and then it uses that to generate the mains waveform when it has failed, or when the mains input has failed. So it needs to first detect a failure of mains and then respond appropriately. Alright. Ready to go. Got this thing plugged in. Okay, power cord inserted. Time for the fireworks show. Yep, so it looks like that was just the transformer we were measuring across. Sweet. Well, I think this means that we're ready to test. First impressions. Let's see. Let's take our test wire. First of all, let's tie earth to ground with the voltage turned. Oh, it's clicking in some of those taps. All right. All right. So now let's just start turning up the current. Oh, you know what? What fun is this without our meter to verify? Ho ho. Okay. So we're going to do a quick short circuit test. We got our multimeter hooked up. We're going to connect it in the 10 amp mode. We are measuring amps DC on the multimeter. Oh. Alright, got it lit up here for you. So we're measuring amps DC on the multimeter. So we're reading 1.77 on the regulated power supply and 1.77 on the ammeter. That is, wow, that is really good. Alright, let's see how this transient response looks. Just going to unplug this. Now we've got 15 volts. Alright, we're going to plug this in. Wow. So what I was looking for there is like an overshoot on the multimeter display, and I am not seeing that. That was really, really fast. I'm impressed with that. Alright, looks like you can read that alright if I let this sit down. So we'll turn up the supply a little more. Stop there for a moment. See what it looks like. Oh, looks like... Oh boy, sorry about that. I know this mic's pretty sensitive to vibration. That probably sounded terrible. RIP headphone users. Yeah, so this is looking pretty accurate so far. More accurate than I would expect. And then looks like we can take this up to 6.16. Here it says 6.18. And there's that temperature controlled fan. I'm liking this so far. I am liking this so far. Looks like it's going to do exactly what we need it to. Alright. However, we have more tests to do. Actually, let me check on the stream health here. Let me make sure that doesn't sound awful with this that close to the camera. Alright, I'm just checking the stream. Okay, that seems to sound okay. I think you can still hear me alright. You can barely hear me over the fan. Alright, I'll just talk loud. I will just talk loud. Okay, so if we give this a moment to cool down, it should, first of all, and then it'll turn off the fan for us. But in the meantime, yeah, it's just harsh reality of turning fans on. I suppose you can hear them. But so now we've got the 15 volt, 15.4, yeah, 15.4. Let's just run this through the whole range. Yeah, it's got 0, 13.76. Try turning it off, then turning it back on. Whoa! That was a grumpy noise. That wasn't exact. Alright, let's do that test one more time. Yeah, difficult to say because it made our multimeter overrange when it turned on. Let's just take this up to the maximum voltage. Looks like it's giving us up to 32, and that display is more accurate than I expected. I am really impressed. I am really impressed. Not necessarily with the specs of this supply. The specs of this supply are fairly standard, really nothing special. But that is awesome. Alright, so I've got a couple loads here. We're going to start with this 10 watt load, and I'm going to turn on the multimeter, or the oscilloscope. We're going to connect this up and look at our voltage waveform. Alright, so we've got the multimeter, or the DMM, hooked up to measure the DC voltage. So, funny thing about oscilloscopes is that they're not very accurate for AC, or for DC. They're very accurate for AC amplitude. They're not very accurate for DC. And it's just, like, you gotta use the right tool for the job. In this case, you got to use the tool that is designed to measure AC or DC. And so what we're going to do is we are going to take channel 1 and we're going to use this to measure our... Oh, this is channel 2. Take channel 2 and we're going to set it to AC coupling, which will allow us to measure the AC noise coming from our power supply, and then we'll use our DMM to measure the steady state accuracy. I'm going to set this over to AC coupling, no bandwidth limit, probe type 1X, and I believe that is the correct configuration. Alright, set to 1X mode. This is a selectable mode probe. Came standard with the Rigol scope. Okay, so here we go. Channel 2's on, waiting for trigger, and the reason why is just because there's not enough noise. We're going to need to zoom in order to evaluate the noise performance. Alright, so now we're on a 10 millivolt per division scale. Wow, we're still not seeing anything. Let's make sure that our our trigger source was not correct. Okay, here we go. Let's zoom in. I would expect that a linear power supply would have incredibly small amounts of ripple. And that seems to be accurate so far. Let's get in this region where we are triggering. This could just be noise of the scope. We're at a ridiculous scale, 200 nanoseconds per division. I wouldn't expect to see noise at that frequency. But let's load this supply and see how that changes. So now we've plugged in cable. We're going to hook that up to one side of this resistor stack. These are all 10 watt resistors. Alright, so now we have loaded our supply. Oh wait, works better when you plug it in. Alright, now we have loaded our supply. We are maintaining an accurate voltage readout, and it looks like this noise has increased in amplitude. Let's see what kind of frequency this is at. This is pretty high frequency noise. Wow. Okay, we're going to add a measurement on screen. Channel 2. Oh. There we go. Oh goodness. Believe it or not, the Rigol scopes were not my first scope. I am much more familiar with the HP Agilent scopes. They've all got about the same stuff in it, but alright, let's get out of this menu. Oh wait. Oh, there it is. Yeah. Oh, wait a minute. There they are. This is what we're looking for. We want... I was looking on the wrong side of the screen. We want the frequency measurement. Okay, so whoop, ground lead popped off. That basically means we've got no coupling of this thing. Alright, things are settling back out. Alright, so now we're at 2 millivolts per division. Pretty consistent noise performance. Actually, we're seeing noise on the order of megahertz? I don't know. I'm still not convinced that's real. Let's perform... yeah. So this is much more accurate. Let's zoom out and take a look at the transient performance of the scopes. We have this set to 10 millivolts per division, which means that when you see the line on this oscilloscope vary by 1 division, so up to there, that means that there was 10 millivolts of noise. So let's go ahead and unplug our load. Alright, we're not triggering anymore. That's... come on. Oh my. Alright. Now I think what this might be is that we have an isolated output right now. Our supply is isolated from ground, so this output voltage is free to vary wherever it sees fit. And since I've disconnected, there we go. Alright, we're back to reality. So I'm going to drop this load on. I'm going to try to capture this event. There. I want to see if that second spike is real. There we go. Alright, we caught a good one. Let's zoom in. So you can see that when we dropped this load on, it's really only, it's not a very large load at all. It's only 150 milliamps. But we're going from a zero load condition, which is pretty much the worst case for a power supply. Our rail voltage dropped by about 30 millivolts. Not great. Not great. But let's try a larger test. Let's set this to 100 millivolts per division. So that's 0.1 volts per division. We'll give it the benefit of that. We'll do 0.05. And we are going to increase our load step considerably. We're going to set this to 10 volts. So I get this set to 10 volts on the dot. And there are DMMs confirming that, yeah, it's pretty close to 10 volts. It's close enough for anything that I'd want to do here. I've had DC regulated supplies that are accurate to 5 digits on a multimeter. So more accurate than our multimeter is here. And that is great. That is a wonderful piece of equipment. And you can really trust that no matter what, when it says 10.0, you got 10.0. But for what I'm doing here and for what you're probably doing at home, 9.97 volts is just close enough. If you've got a circuit with 1% tolerance, yeah, you'd be able to notice the difference. But we're probably operating more in the realm of 10%, 5 to 10% tolerance. And when that's the world you're living in, I mean, 1 volt out of 10. No, I guess that's 1 volt out of 10. It's 0.1 volts. I don't know. So I suppose that's not great. I suppose that's not great. If we're trusting the multimeter, which, if I'm being honest, is not a calibrated piece of equipment, sure, then at 9.97 minus 10 volts, it's 0.03 divided by 10. Yep, so that's 3% error. Error. Yeah. What are you gonna do? What are you gonna do? So, if this is 10 volts ish, and we're about to drop a 5 ohm load, we'd expect to see a 2 amp load step. Let's see how the supply handles a 0 to 2 amp load step. Alright, we might need to expand the Y scale. Got 1 millisecond per division now. Actually, you know what? There's an easier way to do this. We're going to set our trigger level down here, and we're going to set this to single. Then we're going to drop the load on. Boom! It's almost like I know what I'm doing. Alright. So in this case, our supply dropped let's turn off these cursors. Our supply dropped 1, 2, 3, almost 4 divisions. So that's 200 millivolts. That means that we went from 10 volts down to 9.8. It's a fair bit of error. But almost more important to me than the step load performance when it's falling is how this looks when we put it in a lighter load condition. And what that piece of information will give us is, so let's say you have a supply and you have a load that turns off. In that case, you want to be absolutely certain that you're not about to blow up your circuit. And the only way that you know that is if you can trust your power supply to not overshoot. Overshoot's where you set it to 10 volts and it jumps up to something when you pull the load out. Woo! These resistors were getting hot. And so if we're really going to trust it to do that, I think it's time we pull out the big guns. This is my load resistor that we used to boil some water when testing the inverter stage. And so this was 2 in parallel, bringing it to an impedance of 5 ohms. This is 6 of these resistors in parallel, bringing it to a much lower resistance. So let's go ahead and clamp this together and take a look at the performance. This should be pulling approximately 6 amps on the load transient test. Wow, okay. I gotta do that again as a little preemptive. Oh my goodness, tapped. No. Okay, that clipped. So we're gonna need to adjust the scale. Going to need to adjust the scale. So we're going to set this to 0.5 volts per division. Wow. So we dropped by about half a volt when we jumped to a load of about 6 amps. Let's check how accurate that 6 amp was. Anyways, so we've got the positive clip here. I'm going to switch this over to current mode. The voltage readout on this thing is very accurate. We've already confirmed that, but what about the current? Got it loaded. We're seeing what? Oh, there we go, 5.2 amps. Well, there you go, there you have it. That's awesome. That's awesome. Well, we're actually going to leave that plugged in. Maybe not. Yeah, so that is a very accurate current readout as well. A little slow to respond, You can see the multimeter gets there a little faster. Or is that the other way around? Those are very similar. Well, it was a little more quick to respond to changes in voltage at any rate. Alright, we've got a couple more loads to test. But before we do, let's pull this trigger level up here. Let's load it down. Whoa, that is not what I would expect. So when we brought this to a lighter, what this is telling me, there we go. Okay, so when we unloaded this supply, it overshot by about 500 millivolts in the other direction. And this isn't even the heaviest load we can give it. We're going to let these resistors cool off. They're getting a little toasty. We're going to come back to that. In the meantime, let's get our highest voltage load. This is a load that we've been using to test our inverters. We're getting closer and closer to line frequency. And at this low of a voltage, obviously it does not pull very much current, but it's also off right now. So it's pulling about an amp at 10 volts. And let's just go ahead and crank up the voltage. So we're pulling about an amp, 30 volts. We're going to use this to maintain a light load level consistently while we drop this second load onto the supply. This is a more realistic load transient test. When we're doing any sort of load transient testing, it's important to consider what is within the realm of possibility. And in this case, how realistic is a full load step from 0 to a gajillion volts, or from 0 to full current? You know, not very realistic. But a partial load step from something, you know, just kind of always on, like for example, a control circuit that might be pulling, you know, an amp or so, and then a load step might show us something a little different. So let's pull this voltage down to something that does not trip the overcurrent limit. There we go. Alright. Down to something. No, I do not want to trip the overcurrent protection. Alright, there we go. We do not trip the overcurrent protection, but we'll go from approximately 0.7 amps up to full load. Let's start the test. Wow, that's significantly improved performance. Not only is the load step larger, because before we went to about, what was that, 3 amps before? Wow, in this case, we didn't even trip. We did not even trip our trigger. Let's turn down our scale. Okay. Alright. Yes, this went by 1, 2, 3, about 300 millivolts in the negative going direction. Whoa! What's that garbage? Oh, now that is interesting. There's a little bit of instability here. It's difficult to pick up on the camera, but I think you can make that out. So what it is you see when we let go of the supply, it rings up around 300 millivolts and then dips about 300 millivolts. And that might be because this thing's like switching a tap on the transformer. Something. I don't even know. But let's go ahead and do another one of these tests where we trip the overcurrent limit. While this isn't ideal, like it should just ring and come back down to 0. There's something weird going on in the controls of this power supply, but it did settle out pretty quickly, and I'm not gonna bark too much at this supply because I knew going in that this was not the best power supply in the market. I knew this would not have the best transient performance of every power supply on the market. This is just something that I knew when I was coming in. And I knew that I was going to get a $50 power supply if I wanted to pay $50, and that's what I got. This is acceptable transient performance. The ringing's not too extreme, it's quite frankly fine. Alright, so on to a more drastic test. We're going to turn the voltage of this guy up. We need to let this light bulb cool off for a second. And while we do that, let's where are we at? We're at 5 volts per division. Alright. So let's do single trigger. Turn on the light bulb. Single. Boom. Okay. Looks like our time scale needs to be a little longer to fully capture this action. Let's try 10 milliseconds per division. Non-stop. Single. Nope. Still didn't get it. What did we capture? That's it? Alright. There we go. So this is going from about 27 volts down to 10. And wow, that is a really clean transition. Let's make this delta voltage a little bit smaller so we can get a better idea. Whoa! What is that nonsense? What is that garbage? Alright, we gotta do that one more time. There is some kind of weirdness going on in this supply as it recovers from that overcurrent event. This must just be something about the way that they're controlling the constant current mode. It does settle out eventually, but woo, that's not great. Let's see what this looks like in the other direction. So let's see what it looks like when we let up on the load. That looks a little more like what I would expect. So our set point is 15.8 volts. Obviously when we remove the load, it'll want to come up to its set point voltage. Since we're AC coupled, we see that step as the output voltage goes back up to where it should. And then the filter inside the scope kind of figures out its life, and it comes back down to a steady state of 0. So, no weird transients, it just looks normal. Let's give them one more shot on... No, that doesn't look great. Yeah. Consistent performance. Consistently weird. Yeah, something about the transition from the current protected mode to regular mode. It's got some steps. Using just the grid lines here, if we zoom in on this behavior, looks like those are dips of about a volt. So on a 15 volt set point, we're jumping down to like 14 volts. Yeesh. Yeah, that's not great. And the current limit is maxed, so let's just double check what that maximum current is. Yes, we're seeing 6.16. That's accurate. So, all right, conclusion time. Conclusion time for the supply. What are our thoughts? Well, the adjustability on the front is perfectly adequate. I really like the coarse fine knob. If I can't have a digital encoder, this is the next best thing, because you get it, just kind of leave your fine knob halfway. That gives you the full range from about 30 down to about 0, from 6 amps down to 0, and once you find a spot that you kind of like for example 18, then you can take this, bump it up plus or minus a volt. So if you can get the coarse knob within a volt, so 20.7, I should be able to get this down to 20. And if I take this and I connect it to my DMM in voltage mode, I see that that's actually very accurate on 20 volts. If I take this down to 13-ish, let's come up from the bottom, 12.6, maybe up to 13. Again, very accurate. Go down on the low end of the range. 0 volts. Actually, can we get down in the the 1.7 range? Is that achievable? Okay. So we can get down to right around a volt in the 3.3 range. I think that'd be commonly used. That's pretty easy to dial in. It's a little over, but pretty darn close. Get this up to around 5 volts. Yep. Very good performance. I think 12 would be another commonly used voltage. There you go. Current limit adjustability was very granular as well. That'd typically be more, I'll probably put some delineations on here, because that'll be about 3, that'll be about 0, that'll be about 6, add a couple, just so you can kind of shoot it in the, there's 0, 1, 2, 3, 4, 5, 6 type of gradients. I don't think I'd ever really need to be that precise, but if I do, I can always just short positive, negative, and evaluate it that way. Yep, with this now being adopted into our shop as our go-to power supply, I can only think of one way to adequately christen this piece of equipment. And that is to peel off this protective tape. Because you know what? This power supply has been adopted into the EEforEveryone lab family, and we're not sending it back to Amazon. We're going to keep this guy in our shop, and I think it will serve us excellently well during the rest of our projects. So, if you like this video, let me know. Let me know down in those comments. We'll have a recut version for those watching after the fact. I'd say that, believe it or not, I'll double check the math on this. I'd prefer to get this in a percent. They did constant voltage less than or equal to 1 times 10 to the negative 4th plus 3 millivolts, which I presume is voltage set point times 1 negative, so it'd be 0.1% plus 3 millivolts. Yeah, seems about there, but I'll just double check, and I'll throw that kind of overlaid. But before we go, there is one more thing that I wanted to talk with you about, and that is we're coming up on a pretty big milestone for our shop here at EEforEveryone. we're starting to build a pretty nice community of folks that are hanging out in the lab with us and just generally having a good time. And I really appreciate everyone's continued support. Viewership has been steadily increasing, and it's really nice just to see that there's some folks that are interested in this type of content, and that you think that I'm doing a nice enough job to hang around. So I wanted to show my appreciation. We're going to do a bit of a giveaway for those who have been here with us from the start. We're still very small. We've got a long way to go, and we just finished up phase 1 of Project Darwin, which is where we built a prototype inverter using this board. And I'm going to send a fab to at least one lucky viewer. So just go ahead in the comments of this video, just go ahead and let's use hashtag 50 subs giveaway. So hashtag 50 SUBS. There we go. That's what we'll do. 50 subs. Go ahead and put that down in the comments, and I will pick a Twitter follower, MeWe group follower, or a subscriber, and we will send out serial number 2. You will receive serial number 2 specifically. Wow, this camera does not want to focus. Let's try the other one. You will receive serial number 2. Yes. As well, we will be giving away a little bit of our magnet wire. This was our DIY multi-conductor magnet wire. We've got a trimming. So if you want to see up close and personal how we wound our custom transformer, go ahead and throw that same 50 subs hashtag on social media. And of course, the 4 GAN FETs that were blown up during our testing of the inverter due to the short circuit fault in the transformer due to the transient overvoltage event. We will be sending out our broken FETs to you. These were extracted from the main board when we were doing our debug on serial number 1, and I just wanted to share these pieces of EEforEveryone history for anyone who may want them. So if you would like to receive some GAN FETs, serial number 2, or a piece of our first custom transformer, let me know if you would like to receive one of these items, and we will send them to you. Not the transformer. We need this. We need this to build the inverter, but the rest of it, any of this stuff, if you're interested, we will send this to you. So thank you for tuning in this morning. Thank you for supporting the channel. And for those watching the recording and the archive, thank you as well. Really appreciate your support as we've been on this journey towards 50 subscribers. So, without further ado, it's past coffee o'clock, and I need to get to that, so we'll catch you in the next one. Stay tuned for upcoming content. We've got some great videos, including talking through some of the things that you should do if you want to send a board for manufacture. So we're going to walk through the PCB layout process, some things that I had to do in layout when we were planning for automated assembly, as well as some things that we did when we were exporting the design to hand off to a manufacturer to then produce our boards and assemble the parts onto that board. We're going to walk through some of the experiences that we had, and give you a review of the people that we were using specifically for our project. Alright, thanks for watching.